Okay.
So yeah, that's pretty much it. And then yeah, just put everything back in the bag when you're done, and put it back there.
So is that when it's finished, I slide this?
Yeah, you just click this.
I'll click that. Okay.
And then make sure to
Publish on YouTube.
Yeah. I think that's it. Yeah. So
going? Any questions before we get started today? We start homework. Yeah. You take the 5 recommendations I made last week to get started. Seriously, I hope so. Unless you got a free week next week. Okay, good. So today we're going to talk about activation functions for about half the time, and then the other half of the time we're going to look into our first neural networks. So putting together layers of linear transformations with these activation functions. And then we're going to talk a little bit about the power of a 2-layer neural network.
It's universal, right?
It is in some sense universal. So remember the picture here. When our neural networks, the simple picture to have, or like the kind of like prototypical picture to have about neural networks is that we've got a bunch of linear layers, and then in between those layers, we're going to have these activation functions, which are going to be our nonlinear transformations. So if we were just to like compose a bunch of linear layers, we would just in the end have like one big linear function, factorized, so to speak, from layer to layer. But still, that's what we would have, and that's great. But in the end, we would only be able to, like really model linear behavior. So it's these activation functions that introduce the nonlinearities, and then layers of them that allow us to really be able to model these large classes of nonlinear functions. Yeah, is that a question?
If we didn't have activation functions, would it be like piecewise linear then? Or?
No, it would just be a composition. So it'd just be like, what you'd have is in the end you just have another like linear function, but the scalar part, like the matrix part, where you multiply by you multiply the input, that would be a product of a whole bunch of different matrices, one from each of the layers. And so that's what I meant about, like, you can think of it as being factorized. It's like there's one matrix, but it's factorized into this product of matrices, and then all the biases would add up to it like it's into another bias. So you just would get another linear function.
So you could just reduce it just to...
Yeah, it would just be a linear function. Right, so we need the nonlinearities to be able to get the interesting behavior here. So there's actually, lots and lots and lots of activation functions. We're going to look at just like a couple of these, kind of like historical, and then like what's used, and then some interesting kind of variants on these things, but really there's just lots and lots of activation functions that people kind of design for different purposes. So don't think that these are like this is like the library of activation functions. They're just kind of common choices. So we're going to go through and talk about, I guess, all of these, and we'll start with the sigmoid function. So again, like the picture to have here is that we are going to be we have these linear layers, these linear functions, and remember they're taking like some input of think of it as a vector of dimension n, and then transforming that into a vector of dimension m. That could be the same dimension, m could equal n, or it could be different. The activations are typically applied entry-wise. There are some exceptions to that. So like softmax activation does use all of the information, for instance, across all of it uses a sum over all of the dimensions, all the entries in that output to then kind of normalize things. But in general, you're just like applying a nonlinear function entry-wise. Okay. And kind of historically, like, neural networks have been around for quite some time. And for historical reasons, I guess, the sigmoid function is like one of the original nonlinearities used. In fact, it's very, very common in a lot of the older literature, and like things like the universal approximation theorem that I referred to a little earlier, that we'll get to at the end. It is about using activation functions that kind of have a sigmoid-like behavior. And the sigmoid function, there is the definition of a pair. Remember, we actually used that last time when we were doing the example of backpropagation. But it looks like this, right? So if we were to plot it, it looks like this. It has a minimum of 0. It's this asymptote as you go out to more and more negative values. It has a maximum of 1. Again, and you approach that as the argument x increases to infinity, and at 0 it reaches the value 1/2 in between. And the reason why this was used is that a lot of these are called neural networks, and like a lot of the early work and research around these things was basically thinking about actual networks of neurons like you would find in your brain or other like nervous systems, and there are people modeling those things. There have been people modeling those kinds of things for a long time, and neurons themselves tend to have a behavior where they quote unquote fire, or they're electrical nodes of some kind, and they propagate voltage from like the body of the cell out to like the extremities of the cell called dendrites, or called axons, and they connect to the other extremities of other ones called dendrites. Anyways, the point is that when people were doing these kind of analytical models of these like actual networks of neurons, they would often model like the output of a neuron as a firing, like how often was it be like sending these impulses, like per second or whatever. And this sigmoid is kind of like a nice, model of this, where you can think of this as like, no, like 0 is no firing, 1 is like 100% firing, is like maximal firing, and then you're able to kind of move in between there. So anyway, sigmoids became the original activation functions in some sense. So that's great, but actually they're really problematic when it comes to training neural networks, especially as the networks get deeper and deeper. There's really 3 problems here. Anybody want to take a stab at this? Maybe you've already looked at the notes, so if you have, don't give it away, but thoughts? Anybody see problems here? Say it again. Okay. Yeah. So you're referring to like this range right here. Like small changes would have maybe like a large change in the actual value, the output of this activation function. And then it's opposite on the other side, yeah, saturated. So yeah, that's a great point. So like here in like the middle of its range, it's mostly like a linear function, right? I mean, maybe not exactly, but like locally here, this is acting more or less like a line. But as you move away from 0, you saturate. You saturate really quickly. And why is saturation a problem for training neural networks? Yeah, right. So remember that we're using gradients as a way of propagating, information about the loss through the network to update the parameters. And the derivatives, the gradients of these kinds of functions, when you're out, either like you have like a lot of, like this value is large that's going into the sigmoid, or it's very, very negative, you're like nearly flat. So there's really no gradient there. So you're going to compute a gradient. It's going to be nearly zero, and all of a sudden, whatever signal was coming from the loss is just kind of washed out. That's a problem. You need to be able to propagate information. What other things do you see that might be problematic here? What about the actual outputs themselves?
It's similar to 0-1 loss.
Say it again?
It's similar to 0-1 loss.
Similar to 0-1
It's
loss?
only between 0 and 1.
So yeah, so it's only between 0 and 1. Like, what might be problematic about that? That's true. There's some problem here. What is it?
The rapid operation takes time.
The what?
Training time is longer
Well, okay. Why is training time longer?
because there is basically a very little range for loss to update. Update the lead. So
Are you referring back to like the vanishing gradient problem?
yeah, kind of.
Yeah. Okay. So that's definitely a problem. The output's always positive here. So that means that our gradients tend to all have the same sign, whether they're like all of the partial derivatives are positive or all of them are negative. Which means that this is getting at another part of what you suggested. You get slower training times because instead of being able to recapitulate kind of like all possible gradients, you can only get certain kinds of gradients at these layers, and which means that you're going to have to take some somewhat goofy kind of steps, as you're walking down the loss, which is also problematic. Anyways, there are these three problems. One is what we talked about: saturating neurons, kill the gradients; they vanish. This is what we talked about. It's 0 when x is minus 10, or nearly 0. 0 when it's 10, but you have this nice linear range when it's 0. The linear range, by the way, is really good. That's like a nice response. That's like there was a mention of it maybe being problematic that I guess if the slope were maybe too much, you'd have small changes that would correspond to big changes. But this linear kind of activation actually is quite good in the sense of being able to propagate gradients, because it's like multiplying by a constant, right? So it's actually it actually can be, you can control that. That can be quite good. But it's the saturation that's the problem. Related to the conversation we were just having, the outputs here are not zero-centered, right? So everything's positive. So you can only ever get positive values. It's not the end of the world, but it does mean, as I was saying, if you apply these things, it means that your gradient can depending on coefficients in your sigmoid, you're either going to have gradients where all the values are positive or all of them are negative. So so what we're showing here in this picture is where the actual arrows for the actual possible gradients, where everything's positive, everything's negative. So if you have if this were the correct direction to go, you couldn't actually compute a gradient like this. The best you could do is move in this kind of zigzag pattern. You move down first, then you move to the right, move down, move to the right. It's kind of depending on where you get this kind of zigzaggy behavior, which does lead to very slow convergence times, as was alluded to. So that's problematic, and actually having zero mean data or zero mean activations does help with that. Although you'll see that we use ReLUs, and those aren't like that. But and the other thing that no one mentioned yet, but is somewhat problematic, is that there is an exponential in there, and just like computationally, that's a lot slower to compute than, say, an addition or a multiplication or something like that, right? So these days, with modern compute, on GPUs and stuff, this is maybe not so important anymore. But this certainly was more important when the hardware that was being used was not as fast. So yeah, so there you go. Kind of three problems there, and in general, you just don't want to use sigmoid. You will see it every once in a while, but in general, you don't want to use sigmoid activations. Kind of shows that maybe you don't really know what you're doing if that's what shows up in your networks. Okay, so people try to fix this. So one of the early attempts at this was to replace the sigmoids with this hyperbolic tangent, this tanh function. So it has similar properties to the sigmoid in that you have this function that is always increasing, going from 0, or from, in this case, -1 to 1. So we now have the possibility of having negative outputs. The tanh is zero-centered, so it has its, the value in the midpoint of its range at 0. It's 0 at 0. That's kind of nice. So we kind of solved this possible problem around the outputs, not having everything in the same sign. But it still saturates, for large x and for very negative x. Yeah.
What do you mean by saturation?
Yeah, saturation meaning that everything's approaching 1 right here. So it's like, why do we use the word saturation? It's like, if you do chemistry, you keep adding something. So it's like something soluble to the solvent. It can't just keep taking more and more and more of it, right? Like eventually it has a certain capacity, and then you can't take any more. And that's the notion of saturation. It just means that here in this range, things are looking pretty linear. So there's a nice response there. But as you get outside of this linear range, then all the values are the same. Yeah, just like the way that this function works is that, again, you have exponentials in here. So just like it approaches 1, and it's approaches 1 for a huge part of its range, right? After 2 or something like that, it's basically 1. And again, you're going to have these saturated gradients, or these saturated functions. You mean you have the vanishing gradients. Like the gradient here is essentially 0 on this part of the function, the activation function, that part of the activation function.
But doesn't this make it less sensitive to outliers? Because if it was way out there, it's going to generate this giant gradient.
Yeah, it makes it less sensitive to huge outliers in the sense that they all just get assigned the same value. It also makes it less sensitive to things that aren't so outlierish, right? There's nothing statistical here. You haven't computed anything that says outside of this range that we expect to see outliers. It's just once you get outside of a certain range in this function, you're going to have 0 gradients. And that's a problem. We have to be able to propagate back the signal from the loss function all the way through to the beginning of the network so we can adjust the parameters there as well. Yeah?
I think I might be misunderstanding something. So you listed that 0-centered is nice, and in the last example, this is maybe where I'm misunderstanding, because I thought you were talking about the gradient, how that was affecting the gradient.
Right.
Sure. But I'm a little confused because both functions are increasing functions, and so their gradients would still always be positive.
Right.
So I don't understand how 0-centered even affects that. Or maybe I think maybe I'm misunderstanding.
Yeah. So the way to think about that is you have your outputs. So when you're in the linear range, you're essentially getting when you're in the linear range here, not the saturated range, but the linear range, you're essentially just multiplying the inputs by some constant, right? And that becomes your the slope, like the gradient, right? When your output is always positive, then you never have the possibility of getting like you have all the outputs being one sign or the other, and not both. You can't get them. You can't get a mix of these across all the outputs. They're all being pushed to one side or the other. The one side being like the coefficient that might come along inside of the function. We're not really writing these here, but you might have like a learned parameter or something like that. So you're right that like these are all they're all increasing in this sense, but when you push all the values to being either positive or negative, then your data is all on one side or the other, depending on the like the possibility of the coefficient, and and when you take gradients, you're either going to get everything of the same of like positive slopes or everything of negative slopes. When you do this, then you're allowing there to be like coefficients that are also have like a different sign, right? Like you could have some stuff on this side and some stuff on this side of 0, and they would be of different signs.
So if we're treating this thing like a line, if we were to take the partial derivative of this function, if we're treating it like a line, wouldn't it be the slope of the line, like regardless if you're a negative?
Well, you're applying this to like entry-wise to the to the outputs of the linear function, right? So let's see if I can come up with a good example here. Here, let me go to a couple more activation functions where we're actually going to have some values for the like some coefficients within here, and I can come back to this question. It'll be a little bit easier to address because I don't like have the example here. Maybe it's harder to talk about just saying the examples. But yeah, great question. You don't really solve too many problems by going to hyperbolic tangent. That is the case, right? Like you still have these saturating functions, so the gradients go to 0, and you often cannot propagate that signal. And importantly, not to your question, but kind of related to it, like you only have a very small range in here in which you have a linear response. Okay, so what other possibilities could there be? Oh, and by the way, I think I said it, but I don't have it here in the slide. But a hyperbolic tangent is also very, it's more computationally expensive because it's got a couple of exponentials that have to be evaluated. All right. So one day somebody decides to just use this function right here as an activation function. Okay, these are called rectified linear units, or just ReLUs as they're like very often called now. And they just look like this. The function itself is just max with the max of the output with 0, or max of the input, output from the previous layer with 0. So it looks like this. It's basically a line. Just like the identity when the value is positive, and then 0 when it's not. 0 when it's negative. Okay? So like, how is this good? So first of all, the linear range associated with this function is actually quite large, right? instead of it being associated with just some narrow region around, like the midpoint, this is linear for all positive values. It's also really, really, really computationally efficient, right? Like, it's either just the number itself that you inputted. So there's one comparison to make, and that's with 0. Is it is it positive or is it negative? And if it's positive, you just output the thing itself, and if it's negative, you just replace it with 0. And it does have this problem of being not centered around 0. But it turns out that when using these kinds of activation functions, that compared to using something like a sigmoid or a hyperbolic tangent, these things converge extremely fast. Some estimate of like 6 times faster. Who knows on more modern, no one really uses the sigmoid and the tangent except for like possibly at the very end of the network, but never like in between layers. And it's probably much faster now. But the point is that because you have this huge linear range, that you have you're able to get a lot of dynamic response. And these kinds of things came out. Like the use of this ReLU was made really popular in this paper right here in 2012, which something we're going to look at more in a couple of weeks when we start to look at like kind of the history of convolutional neural networks. This network is really important. It's called AlexNet, and it is it won the ImageNet classification challenge in that year, the first convolutional network to do it. And part of the reason why it was able to do that is that it became really efficient to train these things using this kind of activation function. Now, this is not zero-centered, so that's definitely has the same annoyance in terms of like doing the kinds of like gradients you're able to compute, because you get zeros everywhere else. However, let's see. Well, I already answered all these things. Sorry, I thought I was getting a different. Let me just see real quick. Yeah, what I was going to say here was what becomes really important with using ReLUs is the way that these things get initialized. So because there's like huge regions of of space where the activations are 0, meaning there's no gradient at all, no gradient signal at all. You need to initialize your neurons so that you have you're biased towards like having things that will be in the linear range. The way that that's done is by choosing certain initialization functions that get you this kind of put you kind of in this positive regime, so that when you start training, basically there's gradient signal everywhere. Now it's going to be the case that you're going to get zeros at times, but the networks are able to use that. It's actually able to use that and do these tasks nevertheless, which is really interesting. So the efficiency and the large linear range really allow this to work, and good initialization. Now, you don't have to. You can do things like ReLU, but you don't have to make this. You don't have to have zeros here. It's 0 as the value when you have when the x is negative, or when your inputs are negative. A slight variation on ReLU called leaky ReLU basically has everything the same when you're positive, but when you're negative, you have a different linear function with a much smaller slope. So it kind of approximates ReLU, but instead it allows there to be some kind of response. So the response is not, this is like a typical value to use in the leaky ReLU. It's not as, like the slope obviously there is like 100th of the slope on the positive side, but it allows for signal to be propagated through even when the outputs from the previous layer are negative. And this is, again, like there's no saturation here. It's also, it's also efficient, right? Like this is a very efficient operation here. And again, it's going to converge way faster. It doesn't die. There's like not these regions of space where you would get zero gradient. And you would think like, wow, doesn't everybody just use leaky ReLUs as a result? But it turns out that in general, the answer is no. Like you do see leaky ReLUs sometimes, but usually you just see plain old ReLUs. And that's because you tend to get like the same kind of performance, both in efficiency. This is not always, but just like like in general, you get you get the same kind of convergence times, and you get the same kind of output in the end, like the same kind of performance, but you just don't have, I don't know, it's just like less complicated, I guess. And so yes, you'll see these at times, but not always. In general, you can think of this as just like rectified linear units, or ReLUs in general can have a kind of come from a kind of family here where you take the maps of two different functions, one just the identity and the other just a constant times the input, and then that alpha can be used. You can either select it beforehand, or you could actually have it be a learnable parameter, and you can learn that. You could backpropagate to that as well. Again, like you might think that's like really great. Like why not just allow it to do it? In practice, usually this doesn't do any better than just using a plain old ReLU. And this is really true, not necessarily when you're thinking of like a couple of shallow networks, like a couple of fully connected layers, which we'll talk about next. But really like in deeper networks.
So why do we try to remove the negative activations, like Sigmoid also and J2? So what's the issue with the negative values?
What's the issue with the negative activations?
Yeah.
So this is like the same question basically right here. So I haven't gotten quite to the example yet. So I think we actually get to it here in a couple of slides. The problem is that you can't get you can't compute the full array of possible gradients. You can only get things that have where all of your entries have the same sign, and so you can't let's see what's right to say this. Your gradients, you tend to for certain kinds of steps you aren't able, like you'll take a step in a very different direction than you should go, like theoretically, because you can't actually compute the optimal gradient for that function. I'm thinking I have a good slide here to kind of illustrate that a little bit later. So I'm gonna keep going here and get to that. Okay, I think we have a couple of other versions of like the linear units. So here's another one. This is called an exponential linear unit, or ELU. It looks a lot like the leaky ReLU, except that what you have. So again, you just have identity when the values are positive. So you're going to have this nice linear response in this nice range of the output. But when the values are negative, instead of either having those be 0 or the slopes being negative, what you have is you have an exponential that again is saturating, but there's a parameter here that allows you kind of decide, like how, like where to saturate. So it allows you to have some negative values, but it doesn't allow there to be like very, very, very negative values. And usually you can pick a parameter where you get enough response in this section for it to maybe provide some benefits. So it looks like it has benefits of ReLU. You do get saturation of the gradient in a certain region, but it's usually for much more negative values than you would have gotten with like sigmoid or tanh. And you get closer to the 0 mean outputs. And unfortunately, though, because you have this exponential, you got to go back to computing an exponential, which is maybe slowing things down because it's a little bit harder to compute. But yeah, it's another thing in the family of these things, and then something else that's like the full general, like more general than what we've done so far, is to do these things that are known as max out. So you can have these fully learned. It's like having kind of two linear layers within your activation function, and you can learn the parameters, the weights, and the biases, and or not. You can choose them, but typically, if you use this, you'd learn them. Because they're both, you're taking the max of linear functions. You're going to be in linear regimes. You're going to be linear. You're going to have linear output or linear response, which is really great again for propagating signal. There's no saturation here at all, unless I guess for some reason you learn this and these weights became zeros. The only so it kind of has all like I said, there generalizes ReLU, leaky ReLU, kind of has all the benefits there, except that it just doubles the number of parameters you have to learn per neuron. So it's not, in the end, you usually don't get much benefit of doing this. People just end up in the end just using a ReLU. Yeah.
Yeah, so in practice we use ReLU a lot, but then how does it bring in non-linearity to our functions? Because it's a linear function.
But it's not, right? Because it's non-linear because it's zeros and the negatives, right? So it's like the most linear non-linear function in some sense, right? You have this value after which it's 0. So like it's you're bringing max out is the abstraction, the generalization of this. You're bringing together two linear functions, but that don't have the same slope, right? So the whole thing is nonlinear, but it's linear in these two different regimes. So it's very close to being linear, but it is not linear.
We don't even consider the negative value in the first place. So we basically treat them as zeros.
But you do, because the parameters could, in the next layer, the parameters could make your outputs negative, right? It's like you're putting these things together, right? So that's exactly what happens in a network where you have ReLU activations, is that the way it learns nonlinearities is to put certain, for certain input, it'll put, at a particular layer, it'll make some of that output negative, in which case it'll go to 0. In which case, there's no more signal there. Possibly there will, that doesn't mean that in the next layer that there couldn't be non-zero output. That will happen, but it's just like the nonlinear comes through. Actually, if you think about it, it's very easy for the network to kind of learn this, right? It's like either I want there to be a linear response or I don't want there to be any response at all. And that's nonlinear. It's kind of a weak nonlinearity. I think that's your point, but it's still nonlinear, and the network can learn to take advantage of that, and that's what it does. And while all these things kind of generalize it, in the end, it's very simple for the network to learn to just either have linear response or have no response. Yeah.
What's the difference between ReLU and SVM loss?
Right. So first of all, ReLU is not a loss. It's an activation, so it's a thing that kind of happens, in between linear layers. And then in the end, the SVM loss is, there's a max being taken there, so there's some similarities. But in the end, what that's telling you is something like, does the score that does the value that I'm putting into this, is it, for the correct class, is it bigger than the scores for all the other incorrect classes by a certain margin?
So the loss function only applies to the last layer? And
yes, loss functions are they're not activations, but they're like the final quote-unquote transformation, right? The final thing that you do to give you a single number to tell you how well you're doing on the test.
So does the last layer have activations then? Or is it just a loss function?
Yeah, you do, your network's kind of like whatever you want it to be. So there could be an activation, there could be a nonlinearity right before the loss or not. Typically, it kind of depends on the problem, but when you do a softmax before you do cross entropy, which is the loss, that's a nonlinear transformation. Well, it's a nonlinear transformation. And that goes into the loss. Or you might decide not to do that and just have your linear layer go directly into a loss for regression or something like that. So it just kind of depends on the problem that you're working on. But the loss is just the final, the loss is not really part of the network. The network is this thing that takes you from input to output, and then the loss measures how well that output is, how well that function is doing given the output for that input, right? So you have the task. The loss just says for this input, I take that output and I measure something about how well I'm doing on the task. So they're not the same. There's some similarities between the functions themselves in the SVM loss and in ReLU, but it's just because there's a max in there. But the reasons why they're there are just really different. Does that answer the question?
Yeah, does the hidden layers act almost like a kernel function for SVMs?
Does the hidden layer?
Yeah.
Yeah, it can. You can think about it as being, you're making a bunch of transformations, and then really the way, for SVM, you're trying to do this kind of, in the basic binary case, you're trying to do this linear separations. You're trying to put things you're trying to do these transformations, put everything in a space where you can easily separate the positive examples from the negative examples, right? And so yes, it is a kernel method in that sense. It's not true kernel method in the sense there's a dot product that you're generalizing. So it's an abuse of that term, but the general idea of trying to transform your input into a space where there's a hyperplane that divides the examples is the right idea. And that's what's cool. That's what's cool about neural networks, right? Neural networks are just a way of having a bunch of transformations that are being shaped by the task, right? So their whole point is to learn to do transformations layer upon layer upon layer upon layer until the output isn't evaluated for how well it's doing. So it gets to use the task itself to figure out what are the right transformations. Where in a kernel method, you don't typically do that. You are typically guessing beforehand what transformations you want to make, and then hope that in this new space, the task is easier, right?
Is that why SVMs kind of died out and this became the...
The real reason is that GPUs came along and people could start training neural networks, and then on many tasks, they tended to do a lot better. But that's not always the case. It's still the case that for tabular data, a neural network, what's known as an MLP, a multi-layer perceptron. It's basically just a fully connected network. It's usually not better than, say, things like tree ensembles of some kind, gradient boosted trees or random forest or something like that. So it's not, or even an SVM in that case. It kind of depends on the problem. So it's not that these are like, it's not that neural networks are always better. It's that they're because you can now train really deep networks and learn these like lots and lots of these like, interesting transformations. They tend to do really well on the much more complicated problems like picking out a cat from an image, because we can't program that ahead of time. We can't pick the correct kernels ahead of time, or like how to do this in a kernel SVM. But we can learn the appropriate transformations to turn the images into features that allow us to do that. That's the power of them. So they don't really work so well on your tabular data, like I don't know, your list of I don't know, like your demographic data or something like that. But when it comes to things like speech, really more like unstructured data like images and speech, and those kind of things, these far surpass it.
Yeah, what do you mean by the doubling of parameters? Like how does it say doubling the...
Well, in all the other examples where we had a max, there was just usually there was like x here, like the identity function, and then there might have been some learned parameters here, like a learned scalar or something like that. And now you have like both of them. You'd be learning these parameters and these parameters. So there's a lot more parameters to learn in this activation function.
Compared to Sigmoid, you say?
What's that?
Compared to Sigmoid, there will be more parameters.
Yeah, well, compared to like leaky ReLU, or like parameterized ReLU, I should say. Yeah. In fact, it's even more than double. So, yeah. It's essentially like running 2 linear layers for every layer. If you set it up that way. But yeah. It's just the fact that there's 2 linear functions there and you got to learn the parameters for both. Okay. So what does this mean in practice? So you've got to see some activations, ask a lot of great questions. In general, you should just use ReLU. In the end, this is what it turned out to be. And if you read log papers, you'll see that ReLUs are usually there. I will say that most papers on transformers, you'll see that they actually use leaky ReLUs in those. Or actually, not even ReLUs. There's a different kind of. Actually, in transformers, they use something called a Gaussian exponential linear unit, a GLU. For some reason, those tend to work better than an array. So it's not always the case that you see this, but many popular networks that you might use, like you might pull out of a library, the activation is just going to be really loose. And again, it's not because theoretically it's the best activation, because we saw some other ones like leaky ReLU or maybe max out. It's just that in general, the performance using ReLU is usually just as good as maybe using any of these other ones that have learned parameters. And it's because the networks are big, they have lots of parameters already, they're deep, and the network's doing a really good job of learning how to, and they're just the ReLU case of saying either I want linear response or no response. And it just learns to kind of divide up the space of each layer to deal with the problem. And actually I don't know how, the network's not thinking, but the inductive bias there, at least for us, is a pretty simple one. And usually that kind of thing passes to it's also true for just the networks. Like an Occam's razor principle, typically simpler things that capture the needed performance often end up being the better ones to use. So yeah, start with ReLU. You could try out some of these other ones. You'll probably find that things don't change much. Don't do tangent when this says maybe try it out, and please never use Sigmoid, because then you'll just be made fun of by all the people who are doing deep learning with you. They'll say why are you using Sigmoid? You know what you're doing. You don't want that. Okay, so I didn't have a slide in here that actually addressed your question. So I'm going to need to draw something for that. But I think if it's okay with you, what I want to do is make sure that with the 20 minutes that I have left, to get through this part, and then at the end we should come back to that. Okay, so fully connected networks finally. So this is like week 3. We should finally start doing some neural network stuff. This is a deep learning class. Okay, so fully connected neural networks. What do we mean by fully connected? Well, remember what we were doing before? We just had this we had this linear layer. It was a score function. There was only one layer. Now what we're doing is we're going to say, okay, cool. Let's take that. Let's compose it with a couple different operations. Remember, there can always be a bias here, but like lazily, we're not putting the bias terms on here. And in your homework, you will put the bias terms in there. But what we're doing is we're doing one linear operation, as represented by the parameters here in W1. And then we're doing ReLU activation. That's what that max function is about. And then we're doing another linear transformation. Where the parameters of that linear transformation are W2. And here now we've got a couple of different layers for our neural network. So that's what a neural network looks like right there. W2 times max of 0 and product of W1 and X. Sort of not as exciting as like the pictures make them out to be, I guess. But in general, what you have is, like in this 2-layer network, you have your input, you have your transformations, your initial set of transformations, like in this case, just our matrix W1 multiplies X. If X has dimension 3072, which was 32 by 32, then and the output here in this hidden layer, and that's why it's called H, is 100, then what's the dimension of W1? Where we do matrix multiplication like that, where like X is a column vector. Yeah, 100 by 3072. Right, because you're going to multiply on the right, so a column vector, so 3072, so the number of columns in W1 has to match the dimension of X, which is 3072. And then we have to have 100 rows to get an output vector that's of dimension 100. And then W2, so then here you would apply your activation. That would actually be your output H after applying the activation. And then that would be the input now to the next layer, which is parameterized by W2. What's the size of that matrix? 10 cross 100, exactly. We could have been adding biases here, which we're not, but we could have. So what would have been the size of the bias if we were to add it here in this layer? Actually, I didn't understand that, sorry. Did you say 100? Yeah, 100 cross 1, I see what you're saying. Yeah, exactly. Just a vector of dimension 100, and the bias term would be dimension 10, exactly. And so now, and you see it says the value here is S. So if we're doing classification here, what we've done is we've got now the possibility of a nonlinear score function, right, to do classification. So before we were just using one layer here. We could only have a linear classifier. But now, by composing these things and putting like the ReLU or any other nonlinear activation in here, we now have a score function for our 10 classes, so to speak, in CFAR, right? CFAR 10. So input 32 by 32 is this. Output is scores for 10 classes. We now can have a nonlinear score function. So the hope is that we should be able to do better on this task as a result, because the whole function is nonlinear, and we expect the relationship between the pixels in an image and its class to be very nonlinear, right? We don't expect this to be linear at all. Okay, so like, remember this picture, right? This is, I believe, just the same as before, but you no longer like this was these were like the rows from the linear classifier, but you no longer are able to do this because there's no like there's no like matrix that you're looking at here with 10 rows in it and the right number of inputs. So like we're now into a space where like there's some latent features represented by this hidden variable h, and they correspond to features that should be good for doing the classification problem if this thing is being trained to classify, but we no longer can like do this kind of simple visualization. A little bit later, a few more weeks, we're going to look at ways to kind of visualize how classifiers are behaving when we have neural networks with lots of layers.
So that's the weights for W1, right?
No, actually, this is actually like kind of a bad way to do this slide, to be honest, but this is not, because W1, instead of having a row for each of the classes, it's now got 100 rows that represent like some latent variable. And so you could plot each one of those rows, but it wouldn't correspond to plane, car, bird, or something like that. They're just 100 latent classes. And so it's fun to go look at and see what those are, but what they tend to be is like not in a two-layer network, but we'll see like in a many-layered neural network that these tend to be in the first layer very simple kinds of like filters when we're doing convolutional networks, like edge detectors and like color detectors and things like that.
Yeah, they're tricky.
Of course, you can just keep going, right? You just keep going. Like we can make this 3 layers, right? Or what do? We just keep composing it. We take the output from our 2-layer network, we apply a nonlinear activation, here the ReLU again, and then we do this multiplying by a W3, so another linear layer. And we just keep going and going and going. And an implementation in NumPy would look something like the following. You're going to have to do something like this in your homework already. And anyways, the point is that this is what you would do. Can you see something that's really wrong here with this 2-layer network? Where's the activation function being computed here?
The activation function?
Yeah, where's the activation function here? Uh-huh. Yeah, what's wrong here?
Sigmoid.
Yeah, it's a sigmoid. So this is somebody who shouldn't have. This is dumb program. You can already laugh. Go ahead. What kind of a problem is this being set up for? How would you know? Like, what's the loss doing? The loss is taking the output from this 2-layer network, subtracting off like the labels, although it's really the target here, and then it is squaring it and summing it up. So this is actually this is not cross entropy at all. This is not classification. This actually is a regression problem, because this is something like mean squared error. Well, it's mean squared error. There's no mean though. There's a sum on the average. That's why I say it's something like it, but it's proportionate to it. But anyways, yeah. So you can start to look at these things now and like get some sense of what's going on, just because you know a little bit more about like what to expect. In your homework, you're going to do this, but for classification, and you're going to have to do like softmax and things like that. Cool. All right. So
softmax is a loss function, right? Not an activation function.
Well, softmax is an activation, but it's the right activation for cross entropy loss. So sometimes you see, like in this last slide, it said softmax loss. So sometimes you'll see people say that, and it's like just kind of a shortcut for really what it is like you're using a softmax activation to turn your scores into a probability distribution, and then apply cross entropy, which is the actual loss. Does that make sense? All right. Right. So we often like draw pictures like this, and this is like when you think about neural networks, or maybe read about neural networks, you probably see pictures like this. You don't see like what we just did in terms of like the math of doing W3 times max 0, whatever. But this is what you typically see. And the whole notion of fully connected is that the matrices represent, so the parameters in those matrices represent the connections from, from inputs to outputs. So like, multiplying one of the inputs by a certain value to give you the output that goes into the next layer. And fully connected refers to the fact that that matrix containing all those parameters is typically dense. Like there's typically not many, or usually not any zero entries there. So if there's no zero entry, that means that there's actually like a connection from input to out, from all the possible connections between inputs and outputs. And that's what the fully connected part is. We're connecting out every input with every output. In general, this is actually really costly. I mean, like when we have really high dimensional inputs and we have like high dimensional hidden layers and things like that, these are huge matrices, like in terms of just memory and also just like the computation involved. And this is one of the reasons that like networks like convolutional networks exist, is that you no longer have a fully connected network. You're actually doing something like these kinds of dot products, this like linear operation, but it has an inductive bias that we'll talk more about. But it's different. So convolutional networks are on purpose not fully connected. But like in general, neural networks, like the most general neural networks are just these fully connected networks going from layer to layer to layer. Make sense?
Yeah, can you tell how dimensionality changes in these cases?
Sorry, can you tell what?
Can you tell how dimensionality changes? In the previous case, it was just one single neuron on each layer, and then you basically transform the matrix directly. But then you concatenate outputs here. How does the matrix dimension change? Because
the matrix dimension is changing from layer to layer, right? It depends on in a fully connected network, the matrix that goes here is always it has row dimension the number of outputs, and then column dimension the number of inputs, right? And and that's determining like the number of dimensions. Yeah. Okay. Right. So here's like what code might look like. Again, using sigmoids, not good. All right. So you might expect that two-layer neural networks are not very different from like one-layer neural networks, or just these linear functions, because there's just not a whole lot of difference, right? Especially just like that ReLU is not that impressive. And for the case of ReLUs, it's maybe maybe an open question, but it turns out that two-layer neural networks, where we have this hidden layer here, like the latent variables in between, these actually end up being quite powerful, or like quite expressive networks. And that's one of the ways of of talking about that is through what's called the universal approximation theorem. So if notice that the date on this paper is quite old, and this was in the days when like everybody was doing sigmoid type activation. So this applies to here, and there's actually an important reason for it, because this is a nice what's known as a diffeomorphism. You're actually able to prove these kinds of theorems. But anyways, if you have a sigmoidal, so we'll talk about what sigmoidal is in a second, but it basically looks like a sigmoid. If you have a sigmoidal activation function, then functions that look like this, which is basically just doing your linear layer. This has a bias term here. Applying your sigmoid activation, and then having another linear layer, but really you only have the scalar parameters, not the bias parameters here. If this class of functions, which is basically our two-layer neural networks, they're known as, they're dense in the space of continuous functions on a finite interval. So any mathematicians out there know what it means to be dense? Uh-huh.
Do we mean like any open set around the point contains another continuous set?
Yeah, exactly. Right. That's a very precise definition. So another way to think about this is that given an appropriate measure of distance between functions, we can approximate any function, any continuous function on this interval to an arbitrary degree by a function that looks like this, by a two-layer network. So any continuous function, basically, on a finite interval, can be approximated by a two-layer neural network. And there's a lot of wild continuous functions out there. Like it's actually, this is why it's called a universal approximation. There are other sets of functions that are also that can also approximate continuous. They're also dense in the space of the continuous functions on an interval. Anybody know any of the other families of functions that are like this? So polynomials are like this. Polynomials are dense in the space of continuous functions on a finite interval. So that's kind of cool. But it turns out that these things are as well.
Is a Fourier series dense?
Yeah, that's a good question. So, yeah, it's like the space of, in that case, you'd have, when you say Fourier series, yes, in the space of periodic functions. That's right. So continuous periodic functions, that's also right. Actually, it's probably even a little bit looser than that. Anyways, the point is that, so why does this even matter? Well, remember what we're trying to do here is like, we're trying to set up this whole like framework where there's an unknown relationship between our input and our output, and we're trying to like learn that relationship, right? And the function is the relationship. It's the thing that takes us from the input to the output. So it's really great if we can start with a family of functions, these two-layer neural networks, and just know, like from the beginning, that I have the possibility of approximating any one of these continuous functions to like as closely as I want. I can, this kind of notation is just the math notation for saying I get to pick like the tolerance in terms of like how different my two-layer neural network is from here, and I can make it as small as I want, and no matter how small I make it, I can always find one of these functions in this family that is closer than that tolerance. So like that gives us some kind of like assurance that like neural networks are not a bad way to go here when thinking about the family of functions that we would try to learn. By the way, I was going to say something about sigmoidal. What sigmoidal means here is that there is this kind of asymptotic behavior. So we don't really care about what's happening in between it, that's a continuous function. But if we asymptote to 1 as the argument goes to infinity, and asymptote to 0 as the argument goes to minus infinity, then this theorem holds. So, and also continuous. So like our sigmoid function in particular, but it's a little more general than that. So like our tanh function, if we added 1 and divided by 2, would also be sigmoidal. And then you can imagine all kinds of crazy things happening in between, but as long as we have these asymptotes, we're good. Okay, so it's true that like it's not every single function is continuous on a finite interval, but like lots of the things that we care about are. And like piecewise things that are continuous can also be approximated by, like putting the two of these things together, or like however many pieces there are. So there's kind of ways to like easily extend this theorem. The next series of slides is just like pointing, what in that two-layer picture, what do they correspond to, right? So x is the input, The parameters of the layer are the y's and the thetas. Usually that would be the w's and the b's, but we didn't have any control of the way Sigmoid what notation was used. The hidden layer, so like you apply the activation, that gives you the output for the hidden layer, and then this final layer, we just have the scalars for the like the matrix. All right.
So what does I mean? What happens if it's not dense?
What happens if it's not dense?
Yeah.
The theorem says that they are dense. So if these weren't dense, then there would be continuous functions that you couldn't approximate arbitrarily close. Right?
Would that be like a really, really sharp move or something?
Well, the good news is that still is continuous. So you can approximate it. So with the few minutes I have left, I just want to briefly motivate how this theorem works. So it turns out that if you think about like a sigmoid, if you just take the sigmoid, and you really for each sigmoid, like each entry-wise sigmoid, you've got like these two parameters. You got like the scalar and you got the bias. But it turns out like if you play around with these, like if the scalar acts like a gain function, so it's doing something about the slope of the linear regime in between the two asymptotes. It's controlled by this the scalar parameter, like the W. And then the bias. So what happens is, so you have this it's like taking this kind of smooth sigmoid and making it closer. Like the larger that value becomes, the closer this becomes to a step function. And then the bias term basically decides where that what I'm trying to say, where the step happens. Okay? So using these two parameters, you can basically just create a bunch of step functions. And if you're a mathematician, you already know that step functions are already dense in this space. So if we know that we can basically make step functions or make things that are approximately close to step functions, then we're good. But the idea is that if you have kind of two units for every entry, for every dimension, you have two units, one that steps you up and one that steps you back down. Then you can create these step functions, and you can just put a whole bunch of these together in a single layer, right? So for every one of these wiggles, so to speak, you can kind of create a step function that will kind of fit it, and you can just create more and more of these step functions so that you get a closer and closer approximation to those wiggles, right? And that's how it works. It's really just appealing to kind of results that were known earlier. Just we can make step functions, we can make sequences of step functions, and therefore this is going to be dense. So there's some intuition. Great. This we should in some sense be excited. This is good. But in practice, this is really, really bad. Because what's happening then, if the way that this really does this, if the way this really makes approximates these functions is for each one of these kind of wiggles, it's trying to fit in the perfect step function. Then what's happening is that you're basically dividing the space up into these kind of into these step functions, and you're going to need a couple of units in your hidden layer for every single one of these wiggles. And if you have a very wiggly continuous function, then you actually have a hidden layer with a ton of output, or a ton of that's very high dimensional. So actually in practice, this is not good, because you're going to have a network that is with I don't know, it depends just how complicated the function, but possibly millions and millions of these units, in which case this is practically not usable. So yay math said some good things, but in practice, no, that's not good. The way that we overcome this though is with depth. So we trade off the expressivity that you need to do these step functions in one layer into like compositions of these these simpler operations, where we're basically like factorizing out that these step functions and into like features that can be shared by a whole bunch of the different wiggles, so to speak. And there are proofs for how deep these things would need to go, but they don't involve radars because radars are not diffeomorphic, and therefore you can't apply all the nice math that's here. All right. Well, I was going to just kind of go through some of this fun stuff, but I don't have time. But these slides are up on Canvas, and if I clicked on this, it would take you to a link where you can kind of play with some very simple MLPs and see how changing out things like the number of hidden layers, number of units in the hidden layers, the activations you use, how that affects these things. I would encourage you to do that. It's actually quite fun, even if it does use TensorFlow. Okay, so what's the summary here? We talked about fully connected layers. The abstraction of the layer is really quite nice. Just it's nice for like writing code, but just think about this as in terms of a bunch of matrix operations. We didn't really get into the whole thing about being not neural. They are universal, but they're really inefficient, and we overcome the inefficiency with depth. And basically, from here on out, we're going to be spending a lot of time talking about deep neural networks and the power that they have. But through these first couple of weeks, you really have now some of the understanding of the fundamentals of what we're going to be doing. Linear layers, nonlinear activations, losses, backpropagation for computing stochastic gradient descent. And that's that. And let's take. We can come before we can take your question next. But thank you. I'll be here answering